Did we do meth F, all those?
Yeah, that's right.
Did we do, that was the last? Okay. And what we're going to do is we're going to take a look at functional groups. In terms of organic molecules, you can divide those based on composition. A lot of the compositions are the same, carbon, hydrogen, oxygen, but what differs is the structure. So when we look at functional groups, these are certain compositions that are structured in a certain way to give it specific properties or a set of properties that are similar in all members of this group. And so some of the functional groups we're going to look at are hydrocarbons. Hydrocarbons are the simplest organics because they just consist of hydrogen and carbon atoms. But depending on the structures, we have the hydrocarbons that are called alkanes. Alkanes are all carbon-carbon single bonds. Then we have alkenes. Alkenes will have a carbon-carbon double bond. This. And then we have alkynes, which will have a carbon-carbon triple bond. And so we can take a look at some of the alkanes. The simplest alkane is just going to be one carbon alkane. It's a hydrocarbon. You probably already know what this is called. What is this? Or you should know what this is called. Methane. CH4. So we want to know some of the properties of methane, right? But we're just going to focus on one. And that is the redox properties. Talk about redox a little bit. We talk about oxidation states. Normally when you do oxidation states, you do it like this. CH4. And you follow a set of rules. Rules are you sign hydrogen first at what number? The oxidation state of hydrogen and CH4 is +1. We have 4 of those, so it's +4. And that means carbon must be -4. Plus. These are the oxidation states here of that. And so what exactly are those numbers? +1, -4. They're easy to figure out. Anybody can figure them out. But interpreting what they mean, not everybody can do that. Not everybody can do that because maybe they don't care about oxidation states, right? They don't use them, but we're going to be using them. And so let's take a look at carbon. What kinds of oxidation states occur for carbon? Since organic chemistry is carbon-based, let's take a look at the oxidation states of carbon. And see what kind of range we have. What are the range of the numbers that we see? And it turns out that for carbon, the oxidation states range from -4 to 0 to +4. And so this is the range of oxidation states that we see from -4 to +4. And so why do we see that particular range of oxidation states? Can you connect this with something else? Yeah, I see a lot of heads turn to the periodic table. Yeah, take a look at the periodic table and tell me why we see a range from +4 to -4. well, what does a +4 mean? There's a charge imbalance, right? How can you generate a +4 charge in a carbon atom? Subtract 4 electrons. And so if carbon were to lose 4 electrons, how many valence electrons does carbon have? 4. So if carbon were to lose all 4 of its valence electrons, it would have a +4 charge because there'd be an imbalance between protons and electrons, right? If carbon were to have a -4 charge, how could you generate a -4 charge? Give carbon atom 4 electrons. And it has 4 already, and it gains another 4 extra, then it has 8. What's special about 8 electrons? This is an octet. And so either, carbon's going to lose all its valence electrons or fill its valence shell or octet. Does that seem reasonable? And so these are the reasons why we see, this charge variation like this. Carbon's right in the middle. You can gain 4 or lose 4. Well, that's kind of weird because is this a carbon -4 ion? In fact, this is kind of a weird number because what do you do with that weird number? Because when we think about methane, we don't really think about ions, do we? It's not an ionic compound, is it? No, when we think about methane, methane's more of a covalent compound. And with structures like this, have you done formal charge? Formal charge is supposed to be taught in Chem 4, but I think a lot of people don't. You need formal charge to determine what Lewis structure is best. What kind of branching or what they call the skeleton will give you the most stable structure. And so we use formal charges for that. What is formal charge, and how does formal charge actually? How many of you have not done formal charge? Okay. All right. So most of you have done. I think practically all of you have done formal charge. So what's the difference between a formal charge and an oxidation state? Let's say I had a formal charge of +2. What's the difference between a +2 formal charge and a +2 oxidation state? Or a +1 formal charge and a -2 oxidation state. Are they the same thing? So in Chem 1A, we're expected to know not just how to calculate it. How to calculate it, okay, that's Chem 4. Maybe that's a major goal in Chem 4 is can you calculate an oxidation state? Can you calculate a formal charge? You might have used formal charges to predict which Lewis structure is best. You might not have. But, that's one of the most useful things for formal charge. And that's it. But in Chem 1A, we want a little bit more, For example, we want to be able to describe to somebody what an oxidation state is, what it represents. And so let's take a look at the oxidation state versus formal charge. Versus octet. Well, basically, charge is most important in chemistry, right? Charge is extremely important in chemistry. We see this something like this. Let's say your sodium intake is too high. If your sodium intake is too high, is that because you've been consuming too much sodium metal or too much sodium ion? Sodium metal or sodium ion? Sodium ion, right? You don't want to eat sodium metal. Do you know what will happen if you eat sodium metal? I'll show you what would happen if it hits your tongue. You probably have seen this. Let's go to... All right, so your tongue has lots of water or moisture. This is what sodium does when it hits. One thing is it'll melt with heat and then ignite like that. What's happening is the sodium metal is reacting with the water, generating hydrogen gas, and it gets hot enough that the hydrogen gas ignites and potentially explodes, like at the end there. And so obviously, it's the same thing. The only difference is between sodium and sodium ion is the charge. That's it. And chemists are most interested in what's happening with charges because electrical forces are the most important in chemistry, right? And so since we're most interested in charges, we want to be able to figure out what's happening with electrons and what's going on with the charge. When you look at methane, what are the formal charges in methane? Anybody remember how to do formal charges? Formal charge would be something like that. I mean, there are lots of different ways of doing it. And so people have all different, like somebody told me it's the number of protons minus the number of electrons. Well, yeah, that works, Technically, it works, but depends on how you count the electron. Well, I don't care how you do it. Just tell me what it is. What's the formal charge on hydrogen? Well, if you forgot, that's okay. We're going to cover formal charges when we get to Lewis structures. All the formal charges are 0. I circled the formal charges. I put oxidation states in parentheses. This is pretty standard. And so why does carbon have a formal charge of 0 but an oxidation state of -4? How can I have 2 charges? Does it have 2 charges? This is definitely, I guess this is in a way bipolar or something like that, but it's not because these are 2 totally different species, right? And so in Chem 4, they have the, in the textbook, they have the Dr. Jekyll and Mr. Hyde. Have you heard that metaphor? Dr. Jekyll and Mr. Hyde? The same thing, except one of these is Dr. Jekyll. I think this would be Dr. Jekyll, the more sedate one, and this would be Mr. Hyde, a very dangerous one, right? And so is carbon like that in methane? 1 second it's Dr. Jekyll, the next second it's Mr. Hyde. This charge just flip-flops from 0 to -4. Is that what's happening with formal charge and oxidation state? No. So tell me, what do those mean? And or just give me the definition. What is the definition of oxidation state? Or what is the definition of formal charge? Definition. Not how to calculate it. Don't give me some mathematical equation about how to calculate it. Just tell me what it means in words.
I think the oxidation state would be the charge of the element by itself, and the formal charge would be when it's in the compound.
When it's in a compound? Okay. Well, that's good. I'm glad you're thinking about charge. Yeah, not exactly, but getting there. And basically, these are different ways of counting electrons in a structure. Counting electrons in an atom, molecular compound, or whatever. And so it's just counting electrons. When we do oxidation states, we have a very specific way. And so when we're counting electrons, the oxidation state, we'll talk about the definition of that, we make an assumption. We assume bonding is 100% ionic, or a tie. When we assume the bonding is 100% ionic, then we count the electrons, and then we see what the net charge on each atom is. And so what the oxidation state is, or defined as, is it's the apparent charge on an atom using this counting method. And so using the counting method is assuming 100% ionic. Formal charge is just the opposite extreme. You know, if it's not an ionic bond, then it's what type of bond? Covalent bond. And so for formal charge, what we do is we assume the bonding is 100% covalent. And so the way we think about how the electrons are distributed is, you know, in oxidation state, in ionic bonding, this is a winner take all. Winner takes all the electrons. Well, who's the winner? Well, the winner is going to be the more electronegative species. And what is electronegativity? Can somebody remind me what electronegativity is, or how it's defined? You have it? Denser electron cloud? Yeah, it could be, because denser electron cloud could result from stronger electric.
How it pulls the other atom in a compound?
How what pulls?
How strong it pulls the other atom?
Not the other atom, the electrons. And in a way, it could be part of the atom, or it might not be part of the other atom. But how strongly it pulls the electrons. What's the most electronegative element on the periodic table? Fluorine. What are the top 3 most electronegative elements? Fluorine, I heard nitrogen, that's correct. Fluorine, nitrogen, and oxygen. So the top 3 are fluorine, oxygen, and nitrogen. Those are the most electronegative. So whoever's more electronegative, whoever's stronger in the tug-of-war for electrons will win, all of them. When we assume the bonding is 100% covalent, it's 50-50 sharing. And so even though an atom might be more electronegative, like, you know, oxygen versus hydrogen, if you had a tug-of-war between oxygen and hydrogen, oxygen should win because oxygen is quite electronegative. But when we assume 100% covalent, you know, oxygen is going to share 50-50 with hydrogen. And so basically this is the apparent charge on the atom. They have the same definition, apparent charge. Both of these are the charges on an atom. You know, the imbalance between positive and negative charge. Apparent charge on the atom, except this one we assume 100% covalent. Well, if we look at methane, well, methane is pretty close to. If we look at something like water, look at this bond between hydrogen and oxygen. Who's more electronegative? Oxygen. So oxygen is going to pull the two electrons, the bonding electrons, closer to itself versus hydrogen. Because both are trying to pull the electron density towards each other. Oxygen happens to have an electronegativity of about 3.5 versus hydrogen. Now hydrogen is only 2.1, quite a bit weaker. Fluorine, the most electronegative on the periodic table, has a electronegativity of 4.0. This is on the Pauling scale. And so is the bonding 100% covalent here? In reality, is it 100% covalent? In reality? No, because oxygen is stronger. Well, then is it 100% ionic in reality? No, because oxygen is not powerful enough to strip the electrons completely away from hydrogen. 2.1 versus 3.5 has to be a larger imbalance in electronegativities to completely ionize, right? And so what this is, it's actually somewhere between. And so why are we doing this? This is not 100% accurate. This is not 100% accurate. Why are we even bothering with this? The true picture is somewhere in between. And the reason we're bothering with this is because these are the two extremes. One limit, you remember I was talking about, you want to see the whole forest, not just one. If you were just looking at one compound, looking at how the charge is distributed in that, it's quite a bit different than you don't see the whole range of, and so this is looking at the whole range. The whole range is from one extreme, 100% ionic, to the other extreme. If the reality is somewhere in between here, then how do we deal with that? Well, it's too much hassle dealing with that, because what we want to do is we want to be able to use the theory to make some comparisons. And so what you never ever do this. You never compare a formal charge with an oxidation state, right? Because if someone's asking you, what is the biggest charge? And you say, oh, the biggest charge is +2. Another person says, oh, the biggest charge is +4. And they're looking at two different things. One person's looking at oxidation state, the other person's looking at formal charge. You can't compare the two numbers. These two numbers don't compare with each other. It's like, you're in this frame of reference, the Fahrenheit, and this person's in Celsius. You aren't going to compare the two temperatures, so it's 63 degrees. No, wait a minute, it's not 63 degrees. It's a 20 or 18 or 19 degrees C, right? It's just confusing because both of them have the same unit, but you can't compare the two. Does that make sense? And so what we do is we only compare oxidation states with oxidation states. If we go ahead and assume that bonding is 100% ionic for everything, then the numbers have meaning. We can extract some information from those numbers. And so when we compare oxidation states, we compare oxidation states with other oxidation states, and then we can make some useful comparisons. And we compare formal charges with other formal charges, but we never compare between the two. Okay. And so these are just tools. What kind of tools? These are tools to help us understand the properties of these things. Because having non-zero formal charges results in something, and having oxidation states results in something. And so what we're going to do is we're just going to focus in on oxidation states and try to use those to predict something about redox properties. And so this is just narrowing or zooming in just on redox chemistry right now. Redox chemistry is extremely important, right? Extremely important. There's a lot of energy involved in redox reactions. Did you see that explosion in China? The video from that? Huge explosion. If you haven't seen it, check it out. It's amazing how big that explosion was. You would think it was a nuclear reaction rather than a chemical reaction, considering how big it was. They're saying it was not nuclear. If it was chemical, that was horrendous. That was huge. Well, that's redox. Redox, can be huge, those reactions. When you metabolize food, what kind of reaction is that? You metabolize food, that's redox, right? And so let's talk about redox a little bit in the context of these organic. Oh, octet, you know, octet is yet another way of distributing the electrons in a structure. So I think everybody has had lots of practice counting octets, right? So I'm going to skip that entirely for right now. So what can we say about methane? You know, when we look at carbon, you know, carbon can go from -4 to carbon at +4. And over here, when it's -4, you know, redox involves electrons. So we say this is kind of electron rich, on the electron rich end of the spectrum. This should be on the electron poor end of the spectrum. Now, what does poor and what does rich mean? You know, those are very qualitative. And this is what it means. What it means is this. It means in chemistry, we have to do a two-pronged or multi-pronged approach. Actually, I'll just call it a two-pronged approach. You know, we get these numbers from some theory. The theory, you know, these Lewis structures, they call it Lewis theory, but that's also based on the periodic table. Do you know what theory the periodic table is based on? What theory is that periodic table based on? Atomic number theory? No. Actually, I've never heard of that. I haven't heard the atomic number theory. The atomic number, probably the reason I haven't heard it is probably it was probably one of the early theories, you know. The early theories was atomic number, but atomic number theory was disbounded because it's a little bit more than just the number of protons. You know, people thought the number of protons would dictate all the properties, so you can base it on that. But it's a little bit more complicated. It was well, it's the periodic table is based on quantum mechanics, quantum physics, quantum chemistry. Quantum deals with how the electrons are arranged in there. And so these numbers come from quantum, right, the theory. But how do you interpret those numbers? We can get those numbers, but what do those numbers mean? Can you put it into any kind of perspective? And so this is why there's a two-pronged approach. The two-pronged approach is you can't do everything by theory, and you can't Google everything. And so you know, over the summer I was reading something about some elementary schools. They want to get rid of memorization entirely, and I thought, wow, what a bad idea. It was a very bad idea because, you know, you should teach the kids that they need to do memorization, but they need to do memorization in a certain way. You know, you don't want to have rote memorization where, okay, some people, like in Chem 4, they ask me, do I need to memorize the activity series? Do you remember the activity series? Can anybody tell me what the top of the activity series was? Most active element? Sodium? Sodium is a good guess for sure. But you know, I say no, don't memorize the activity series element by element. That's kind of a waste. Instead, what you should do is you should look at or look for patterns. Do you see any patterns in reactivity in the activity series? And then it's very simple, because at the top of the activity series are the alkali metals, right? And then if you really want to get into it, then you look, wow, the alkali metals are inverted. You know, so it's not sodium. You would expect sodium maybe at the top, but it's actually rubidium and then potassium. And so it's actually upside down. And so why is it upside down? That's another pattern, except for lithium. Lithium is the oddball. Lithium is at the top, and then the rest are inverted. You know, and so those types, and then the coinage metals are way down low. And so, you know, I don't mean memorization. You get out the flashcards, you memorize things. You know, when you got a lot of data, you know, the activity series, no way do you want to memorize that because, you know, here we have an abridged version of that activity series. Your Chem 4 activity series was nothing, right? Let's take a look at this because we're going to be using this chart quite a lot coming very soon. You look at a chart like this, and the chart in your book is much bigger. If you go to Appendix B, the chart in your book spans like 4 or 5 pages. You look at a chart like this and you see, oh man, that's just too much data. And it's like data overload. Is there any way you're going to memorize this? No. Or why would you bother memorizing this? But instead of memorizing this, you know, what you should do is you should start to try to do some data reduction. Have you ever heard of data reduction? Data reduction is, you know, scientists collect tons and tons of data, right? And you got all this data, what do you do with it? You don't want to leave like 60 pages. When you have like 60 pages of data, you don't want to leave it like that. Okay, look at the data on page 55, right? What you want to do is you want to try to reduce that data by looking for trends, right, and patterns. And so here's the activity series. At the top of the activity series is lithium, right? And then rubidium, potassium, calcium, sodium, magnesium, aluminum, etc. And so you try to look for patterns there. You aren't going to be able to get everything because some of these things, you know, are just, but you just want some general things, and you know, that's the type of memorization that you need to do. You need to do some memorization in order to understand. Well, somebody says, I don't need to memorize that, I can just get that from theory. Well, how good are you at quantum mechanics? You know, okay, do it for me then. Tell me what's going to be at the top of the list, the activity series. Or they'll just look it up, you know. Look it up. Well, unfortunately, you can't do that on, like, I guess you could. I haven't seen it. I haven't seen it done. Maybe they're doing it now at conferences, you know. Just a minute. Let me Google that or something, get you your answer. But I don't know if you've looked at Yahoo Answers or some of those. You know, some of those answers are just awful. Those are not peer-reviewed. You know, there's no referee checking them. You know, it's just somebody blurting out an answer, and a lot of them are bad. But anyway, the way we put this into context is we do a little bit of memorization, you know, and we look for patterns or something that we can remember that we can put this into context. And so something like this is done by observations. You know, you look at a whole bunch of observations, and this is how you accumulate experience. You know, they call it experience. Experience is just having a lot of like little facts known. Like, you know, if you take a car to a mechanic who has like 30 years of experience, right? Then they know a lot of things because they observed a lot of things, saw a lot of things, right? They aren't just Googling, okay, what's this problem that you're having there, and maybe the answer is there on Google. Well, the same thing. What we're going to do is we're going to accumulate those little bits of factual knowledge so that we gain experience, because there's no way you can do this 100% by theory. But the problem is okay, memorizing a whole bunch of little facts, you know, it's only useful up to a point. You know, you see patterns, you see trends, but if you really want to minimize the amount of memorization, then you have to understand some theory. That way you can make some connections and better understand these patterns. You don't actually have to understand theory. You can just base it on pattern. You know, if you know the patterns, maybe the theoretical knowledge isn't there. And so it's this approach where we use patterns, trends, or theory and supplement that with factual knowledge. Okay. And so we have to gain some factual knowledge. You know, what does carbon in a -4, what does carbon in a +4 mean? You know? And so let's look at some examples of this right now. You know, with these hydrocarbons, one thing about these hydrocarbons, and one chemical property of methane you should know, is methane is flammable, right? Is methane very stable? For example, if I filled this room up with methane, would you feel comfortable or uncomfortable? You know, methane actually has no odor, right? But they put some kind of odorant in there. It smells awful. You could breathe methane, not even know you're breathing. You don't want to asphyxiate yourself. And so let's say I start filling this room up with methane, but not enough to asphyxiate ourselves. You'd feel pretty uncomfortable, right? Because methane, is it stable or unstable? Unstable. So you have that bit of factual knowledge, you know? Somebody knows, oh yeah, methane, that's unstable. Keep it away from sparks, right? And so when we do methane, we already did this, right? -1, actually +1, -4. We've got the oxidation states. All right, this is the Chem 4 method. In Chem 1A, we might have to get a more detailed oxidation state by doing structural analysis like this. And so when we look at the structure, carbon versus hydrogen, who's more electronegative? Carbon. Carbon takes all. And so carbon took all the electrons from hydrogen. And so that leaves hydrogen with how many electrons? None. Hydrogen is supposed to have 1 electron. If it's lost 1 electron, then it's short. And so there's a positive nucleus that's not balanced. So this is +1, +1, +1, +1. Now carbon took all the electrons, now has 2, 4, 6, 8. Carbon's supposed to have 4 electrons, now has 8 electrons. It gained 4 electrons, which means its charge is now -4. We call that electron rich or electron poor. Which side of the spectrum is it? On the electron rich side of the spectrum. Then we react this with this. What's this called? Oxygen. A winner take all. So oxygen versus oxygen, who wins? Oxygen versus oxygen, which one's stronger? Neither is stronger, right? This is a tie, so there's nothing we can do. So we gotta have a tie here, which means how many electrons does each oxygen end up with? 2, 4, 5, 6. How many electrons is oxygen supposed to have? 6. So it ends up with 6. It's supposed to have 6. That gives it a 0 oxidation state. This one's the same. This is 0. We could have done this using the rules. You know, the rules are the oxidation state of an element in elemental form is 0. What is that? Is that electron rich or just fine as is? Maybe, what do you expect the oxidation state of oxygen to potentially vary from? From what to what? Look at the periodic table and tell me what you think the oxidation state might vary from for oxygen. Two to 0? I heard that, but no, I don't agree with that range. What do you think the range of oxidation states for oxygen is? +2 to -2? That's getting better. +2 to -6? -2. -2 to +6? Yeah. Why -2 to +6? Gain 2 electrons.
We can offset or it needs to lose 6 to
Yeah. Okay. It can either gain 2 electrons and be like neon, or lose 6 electrons and be like helium. Do you see that? So that's the range we would expect. All right. Now oxygen is 0, so maybe it's just okay as is, right? It's like, what else has an oxidation state of 0? I know something else. Diamond. You know, carbon atoms in the diamond form have an oxidation state of 0. And so here, oh yeah, this has an oxidation state of 0, this has an oxidation state of 0. Is it okay to compare the 2 oxidation states? Yeah, because they're oxidation states. We're comparing oranges with oranges, right? We don't want to compare oxidation states with formal charges. And so does that mean diamond and oxygen are kind of the same because they have the same oxidation state? Oh, I know something else that has an oxidation state of 0. Sodium metal. Sodium metal has an oxidation state of 0. And so since all 3 of these have an oxidation state of 0, that means all 3 are exactly the same. Right? No. Wrong. Totally wrong. And how do you know this? Did quantum theory tell you this? No. You know what told you this? What? Experience told you this. In other words, you had some facts memorized based on your observations of past events. And so we need some factual knowledge here to help us. And so, you know, just because it's 0, it depends on what element we're looking at. A 0 in oxygen is different than a 0 in these. And a 0 in sodium is different than these, right? And so there's no way we can just look at the numbers and say, oh, based on this number plus 2, that means this is going to happen, right? The only way we know is we have some kind of frame of reference. And the reason is you would think quantum mechanics is easy. Is quantum mechanics easy? Did they teach that in Chem 4? No, because it's hard. The mathematics is very difficult in quantum mechanics. It's not easy. And so to be able to expect theory to tell you everything is a little too much of a high expectation. But we see reactions as what happens when methane and oxygen react? What do we form? What do we form? Carbon dioxide. And water. What do you think is a more stable mixture? Methane and oxygen or carbon dioxide and water? If you mix carbon dioxide and water, do you have to worry about flames or potential explosions? You know, like in New York City, there are some pretty big methane natural gas explosions that destroyed a couple of buildings recently. Did you guys hear about those? Yeah. Caused a lot of damage. And so methane and oxygen is not a stable mixture, whereas CO2 and water, is CO2 pretty stable? Is that very explosive, you say? Highly reactive? No, heck, they use CO2 in fire extinguishers, right? CO2. Did I talk about don't use a CO2 fire extinguisher in a metal fire? Why? Well, we'll talk about that. But let's take a look at the oxidation states here. Look at the oxidation states, winner take all. And so oxygen versus carbon, who wins? oxygen. And so oxygen took all the electrons, so it means that 2, 4, 6, 8 electrons. It's supposed to have 6 electrons. It ends up with an oxidation state of -2. Carbon ends up with nothing. It's supposed to have 4, so it's got a deficit of 4 electrons. So it's going to be +4. +4, we called that electron poor. But it's all relative because, you know, CO2 is pretty stable. It's like we've seen +4 in carbon in other compounds, like for example carbonate. Carbonate's a pretty stable ion, well, fairly stable. And what is the oxidation state of carbon in carbonate? Here we could use the rules. -2 for oxygen times 3 is -6. -6 plus 4 gives us -2. And so this is +4. We see +4 in a lot of carbon-containing compounds, which makes me think that +4 is fairly stable. +4 is fairly stable unless you react it with something that's very electron rich, like the active metals. Metals, you know what one of the properties of metals? Metals tend to lose electrons when they undergo chemical reactions, and they tend to form cations, right? And so you don't want to use CO2 in metal fires because CO2 has the potential to react with metals and take electrons because carbon is somewhat electron poor. And you would think with the +4 it's highly poor, but no, it's not that poor. Only metals. You know, you could use CO2 on other things and you wouldn't have to worry about it too much. Whereas, let's say oxygen in a +4. If oxygen were in a +4, watch out, because that would be a very dangerous chemical if oxygen were in a +4 state, because oxygen definitely does not want to lose. In fact, oxygen, even in the 0, is unhappy because, take a look at water. Is water stable? Water very stable? Yes, water is very stable. What are the oxidation states? Oxygen versus hydrogen, who wins? Oxygen, -2. Hydrogen, +1. And +1. And so when we look at this, it seems that oxygen in a -2 oxidation state forms pretty stable compounds. So maybe oxygen's the happiest with a -2 and kind of unhappy with a 0. And it would be very, very unhappy with a positive. Whereas, you know, carbon's okay with a +4 here. And so where do we learn this kind of stuff? Where can we put these numbers into perspective? Well, you have to memorize this stuff. That is, well, how do you memorize? You don't sit there with flashcards. You just do some of these things, and just by observation. You see these things repeatedly, and you can put things into some kind of context. But, you know, it's not easy because the person with 30 years of experience has had a lot of observations, right? A lot of the times it's the same stuff over and over again, but for you guys who are just starting out, you have to, you know, pretty much cram like 30 years worth of observations into a semester kind of deal. But it's not that bad because, you know, we do a lot of reactions. This one is done. Look at this. Pretty big explosion there. I mean, it's like a pretty big building here, tall building. Can you believe that? So when you think it couldn't get worse, it's worse. Yeah. Well, anyway, there's lots of videos of this. There's a lot of people end up dying, but I haven't been following the story, to be honest, but apparently there's some calcium carbide. Calcium carbide has a formula like this. It's solid. Calcium carbide. A calcium carbide, is that a covalent or ionically bonded compound? What would your first guess be? Or you probably already know. Metal plus non-metal is ionic. So it's ionic bonded compound. For ionic structures, we represent those differently. You know, ionic, we show the valence electrons. So this would be the calcium ion. Here's the carbide ion. Carbide ion has 8 valence electrons and a 4- charge. It's carbide. There's another calcium. So this is ionic, we form an ionic lattice. So let's represent a calcium ion like this. This would be a carbide ion, calcium ion, carbide ion. Anions are usually bigger cations and generate some sort of structure like this. What do we call this structure? Ionic lattice, good. So we have some ionic lattice like this. But you look at this, you know, calcium ions, are those pretty stable? You know, is calcium okay with a 2+ charge? Based on your experience, is calcium okay with a 2+ charge, or is it unstable with a 2+ charge? That's its charge. When you buy calcium supplements, is it calcium metal they're giving you, or calcium 2+ ions? Calcium 2+ ions and some anions. And so you take calcium, you're taking, that's calcium 2+, no big deal, that's stable, right? How about carbide? Is carbide stable? It doesn't appear so, because carbide is quite electron rich or electron poor? Rich. Quite electron rich. But you know, if you go to the tool store, you'll see silicon carbide. You seen silicon carbide? Silicon carbide is like a very hard, abrasive material, and very stable. You know, can withstand high pressures, temperatures, and that kind of stuff. Why would silicon carbide, you know, if carbide's unstable, why would they use it in silicon carbide? Because of this. You know, calcium carbide is ionic, whereas silicon carbide is covalent. And so silicon carbide doesn't really have nearly the -4 apparent charge that calcium carbide does. These two carbides are totally different, you know, even though both of them are going to be -4. The silicon's +4, carbide is -4. Well, that's its apparent charge. In reality, since the bonding is quite covalent here, its real charge is going to be quite a bit less than that. And so it should be a lot less reactive, whereas calcium carbide is going to be highly reactive, right? And so maybe somebody's thinking, okay, I got a carbide fire, you know, I know silicon carbide, we use that in cutting tools, and so spraying water is probably okay, you know, if your silicon carbide caught on fire or something like that, right? But here they sprayed water on calcium carbide. Well, if you're thinking sodium, you know, sodium metal we call electron rich, because when sodium reacts with water, you know, it gives up that electron, water takes that electron, forms hydrogen gas. Well, when calcium carbide reacts with water, this is a well-known reaction. Because when calcium carbide reacts with water, this is called the miner's headlamp reaction. In the old days, you know, they didn't have batteries. And so the miners, you know, that would go underground would have a headlamp here. And the headlamp, they had a bottle in which they had calcium carbide and water. And then they'd slowly let the calcium carbide react with the water, slowly. And when that happened, it generates acetylene gas. Acetylene gas looks like this. It's acetylene. This is what we call a, did I talk about alkanes, alkenes, and alkynes? This is an alkyne. And the name of this is ethene. No, excuse me, not ethene, ethyne. Or its common name is acetylene, and everybody knows it by its common name, acetylene. They'd ignite the acetylene and generate a flame. But when acetylene reacts with oxygen, you know, it's flammable. It can combust. And so you use acetylene in torches, welding torches as well. And so let's take a look at the oxidation state here. And so we're going from carbide, where carbon is in the -4, to acetylene. Acetylene, what's the oxidation state on carbon in acetylene? No, not yet. Carbon versus hydrogen. You know which one's more electronegative? What would you guess is more electronegative, carbon or hydrogen? Carbon. Actually, not by much. The electronegativity of hydrogen is 2.1, carbon's like 2.5. So it's not a huge difference. Carbon wins. Carbon versus carbon? It's a tie, so just count them up. 1, 2, 3, 4, 5. How many electrons is carbon supposed to have? 4. So it's -1. It has an extra electron. Hydrogen's +1. So this is -1, this is +1. This is symmetrical on both sides. Well, -1, what would you say, on the electron-rich side or the electron-poor side? Maybe on the electron-rich side, because you know they have oxyacetylene torches. Oxyacetylene torches react acetylene with oxygen. And it depends, you know, you want to get just the right amount of oxygen. So you have 2 valves. You can adjust the acetylene and you can adjust the oxygen. And you probably have done this, you know, to get the right ratio using a burner. The flame. Do you want a yellow flame? No, is a yellow flame good? Did you guys do this experiment in Chem 4 where you generate a yellow flame and then you put a white evaporating dish above yellow flame? And then you look underneath and look. That yellow flame put a whole bunch of black deposits. Have you done that? Okay, otherwise I'd demo. It's pretty easy demonstration. But a yellow flame is not enough oxygen, and so we have incomplete combustion. The black coating is what we call soot. Soot is just carbon particles. What's the oxidation state of carbon in soot? 0. And so not enough. And so what you do is you open up the air a little bit, get more air in there, more oxygen to get better combustion. More complete combustion. And so you enter a little bit, but you might also generate this. You got to be careful in the lab because you don't want to generate too much of this. This is carbon monoxide. Carbon monoxide forms from not having enough oxygen. We call this, again, incomplete combustion because what is the oxidation state here. Oxygen is -2, carbon is +2, right? And so we need a little bit more oxidizer. You know the term oxidizer, where it comes from? Oxygen. Is oxygen the most powerful oxidizer around? Or is there only one oxidizer? That oxidizer is oxygen? Yes? No, there are many oxidizers. In fact, there are oxidizers more powerful than oxygen. Can you name one oxidizer more powerful than oxygen? I can. Fluorine. In fact, let's go back to this chart over here. If you spend some time looking at this chart over here, this chart is a table of oxidizers and reducers. On the left side of this chart, we have the reducers with lithium at the top. On the right side of this chart, we have the oxidizers. And fluorine's at the top of the heap for oxidizers. When you look at fluorine, it's here. Oxygen's up here. Fluorine is stronger than oxygen. In fact, to give you an idea of what happens, and we got iron metal here. You know, this iron metal is slowly being oxidized, rusted by oxygen, right? If I took this piece of iron metal and put it into a stream of fluorine gas, you know what would happen? If I took this iron metal and put it into a stream of fluorine gas at room temperature, it would ignite spontaneously, burst into flames, basically. Not only iron, but stainless steel. You know, stainless steel is very resistant to rust, but if you put this into a concentrated fluorine stream, you're going to ignite the stainless steel. It's going to catch on fire because fluorine is a much more powerful oxidizer. So much so that, you know, the people who work with fluorine, they have the fluorine chemist handshake. The fluorine chemist handshake is this, you know, because they've lost 2 fingers due to some bad reaction with fluorine or explosion. And so anyway, here we're going to try to combust this. If we combust acetylene completely, what should we form? You know, this is incomplete combustion, incomplete combustion. This is what we call complete combustion. We should form CO2 and water. CO2 and water. With complete combustion, what are the oxidation states here? -2 and +4. But you know what? I'm just going to keep opening this. Keep opening this. Get more air in there. And then I don't want just complete combustion. I want ultra complete combustion. Carbon trioxide. Or ultra complete combustion. Carbon tetroxide. Or carbon pentoxide. Why stop there? Carbon hexoxide. Carbon hep oxide. Where does it stop? Where does the oxidation process stop? And why? What's the oxidation state of carbon here? Oxygen is -2. -2 times 7 is -14. That means carbon must be +14. So apparently it's lost 14 electrons. But how many electrons does carbon have? It has 4 valence electrons and 2 core electrons for a total of 6 electrons. And so something that has 6 total electrons, is it possible to lose 14? And so this is impossible, 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 impossible. How about this? Here, this is possible, right? Here we lost all its valence, and if we lose the 2 core electrons, then we can generate carbon plus 6. But how hard is it to lose a core electron versus it's extremely difficult. The core electrons are quite unreactive. And so carbon trioxide isn't going to happen. And so it stops at carbon dioxide. This is why we say the oxidation state range of carbon is from -4 to +4. To go to +6, you would need an exotic oxidizer. Are there oxidizers stronger than fluorine? Well, the strongest one on that chart is fluorine. Are there oxidizers stronger than fluorine? The answer is yes. Those are some of the common oxidizers there, but there's going to be some exotic oxidizers. And oxygen certainly isn't enough. Oxygen is not powerful enough to oxidize the core electrons. But if you had some super exotic oxidizer, you might actually be able to knock off the core electrons as well. Take those. Well, anyway, just this reaction, can you imagine how much energy that released? That's a lot of energy. Acetylene is actually dangerous stuff, as people know, and calcium carbide too. If you go and look at miner's headlamp, you'll see little mini explosions. There. As the calcium carbide hits the acetylene. Well, what we're looking at here is, okay, we looked at methane. How about ethane? How are the properties of ethane? Well, they're going to be comparable to methane. What are the oxidation states here in ethane? Has somebody figured it out yet, or still no one's figured out how to do it? Has one person figured it out? Okay. -1? No. Uh-huh. -3. -3. How did you do that?
I just boxed it and counted it.
You boxed it and counted it? Yeah. You do it. 1, 2, 3, 4, 5, 6, 7. 7 electrons. It's supposed to have 4 electrons. It has extra 3 electrons, so -3. Hydrogen? Not 0. 0 means it has 1 electron. It's supposed to have 1 electron. It's +1. And so this is going to be -3, that's 1, +1. Why do I do it like this? Isn't it easier just to do it like this? Like you learned in Chem 4? You learn in Chem 4, this is C2H6. This seems just a heck of a lot easier. +1, +6, +6, -6. -6, you have 2 of them. -6 divided by 2 is -3. Isn't that easier? Right? It's easier, but you lose some structural information. And so that's why in Chem 1A I want you to do it like this, even though, you know what, this is not in the book. If you're expecting to see this in the book, then it's not there. You have to learn it on your own, basically. All right, so ethane, electron rich, electron poor, what do you think? Electron rich, because ethane is highly flammable. Fuels are the electron rich Oxidizer is the electron poor part. You take a fuel and oxidizer, you get a redox reaction. Electron rich part loses electron, electron poor part gains electron. That's a redox reaction. And so ethane should be similar to that. What's the next one? Propane. Right, this is propane. Also electron rich. And then let's look at some alkenes. For example, this. We'll look at the simplest one. This is called ethene because an alkene has a double bond. And so we just changed the name. You see, you use the parent name and then the functional group, ethene. And then we have this one. I know how many hydrogens to put on here because of the bonds. Carbon likes to form a total of 4 bonds. This is called propene. And then let's take a look at this one here. How about this one? This is called butene. Butene. How about this one? This one's also called butene. And since both of these are called butene, we have to differentiate between the two. And the way we differentiate between the two is this. We number the carbon atoms. And so but is a 4-carbon chain. So we number the chain 1, 2, 3, 4. 1, 2, 3, 4. Okay, this one we call 1-butene because the double bond starts on carbon 1. This one we call 2-butene because the double bond starts on carbon 2. And what would this one be called? What would this be called? It looks like 3-butene, right? Because the double bond starts on carbon 3. But it's not actually 3-butene. This is the same as 1-butene. Because if I flip it over, or if I number it from, rather than left to right, I number it right to left, it doesn't matter. You know, this thing's moving in space anyway. And so this is 1-butene. And so what we do is we always choose the lower number. Choose lower number for this. But basically, we look at the oxidation states. What's the oxidation state of carbon here? 1, 2, 3, 4, 5, 6. Minus 2. Is that electron rich? Yeah, ethene's flammable. Propene's flammable. Butene's flammable. All these are flammable. These are electron-rich species. Hydrocarbons are. You know, and then we saw acetylene with a triple bond, or ethine. Well, that's flammable stuff too. All right. You know, the next thing we look at are alcohols. Are alcohols flammable? And the reason I want you, we're going to look at simple alcohol. Actually, 2. Do I have enough time? Yeah. The simplest alcohol is a 1-carbon alcohol. This is called methanol. It's ane because it's all single bonds. It's all because it's an alcohol. So we see the structure in the main name. It's also called methyl alcohol. Methyl in organic chemistry is given to a CH3 group. The CH3 is not complete. There's a dangling bond here. And so this is a methyl. You attach it to something. It's a methyl alcohol. This is also called wood alcohol. Get in time. What are the oxidation states here? The carbon is going to be 2, 4, 6. 6 is minus 2. This oxygen is minus 2. The hydrogens are plus 1, plus 1, plus 1, plus 1. That's it. Does methanol, what would you say, electron rich because of the carbon or electron poor because of the oxygen? Electron rich. When we look at this, we could have done this using the formula. The formula for this is CH4O. You assign hydrogen first at plus 1, oxygen's minus 2. This means this has got to be minus 2. Here. Let's go to ethanol next. It's electron rich. And ethanol, look at the structure like this. Time. Ethanol has a structure like this. What are the oxidation states here? When we look at the oxidation states, well, maybe it's easier to do it off the formula. It's formula C2H6O. Hydrogen's plus 1, oxygen's minus 2, so this plus 6 minus 2 is plus 4. Plus 4 divided by 2 gives me plus 2 on each. And so it looks like the carbon has an oxidation state of plus 2, each of those. But when we look at the structure, what's the oxidation state on this carbon here? There's 2, 4, 6, 7. It's minus 3. And so this says the oxidation state's plus 2, but this says the oxidation state's minus 3. Something's wrong here, isn't it? But then I look at this carbon here, and when I look at this carbon, it's 2, 4, 5. Oh, this carbon's only minus 1. And so one of these carbons is minus 3, the other carbon is minus 1. You see? What we see here is just the average. The average carbon has an oxidation state of plus 2. Well, sometimes we don't want the average. We want more structural information than averaging things out, right? And so this is why I'm asking you to do this other method here. We'll talk about alcohols a little bit more next time, but I need you to start memorizing stuff over the weekend. And this has to do with ions. And so I'm going to write a rapid list of ions that we need to memorize. Cations. You know, we have monatomic cations, single atom. And we have two categories. We have fixed charge. Fixed charge, if we look at the periodic table, group 1, group 2 are fixed charge. And then scandium, what charge do you think scandium is? Plus 3. And we have aluminum, what charge is aluminum? Plus 3. And so these are some fixed charge, but there are 3 in the middle here that form this kind of elbow here. And the 3 in the middle, silver, what charge is silver? Silver is always plus 1. Zinc is always plus 2. Cadmium is always 2 plus. Chem 4 also throws nickel in here, but I eliminate nickel because, you know, 95% of the compounds of nickel are plus 2, but there are quite a few compounds of nickel 3. And so I don't want to put nickel as a fixed charge. And so we call this, you know, for example, silver ion. What is silver ion? Silver ion is Ag+. You should know that. Now, they're going to be monatomic variable charge. So let's take a look at the variable charge. Variable charge is pretty much everything else, right, for the cations. And so if we have Fe2+, then we call this iron Roman numeral 2, right? Fe3+ is iron Roman numeral 3. As far as polyatomic cations go, polyatomic we have ammonium, NH4+. Is ammonium electron rich or electron poor? It looks electron poor because of the positive charge, right? But actually it's electron rich. It's electron rich because this poor rich stuff comes from oxidation states. So the oxidation state of hydrogen is plus 1. That means nitrogen is minus 3. Hydrogen's okay in plus 1. And so this positive charge is because of the hydrogen. But hydrogen plus 1, no big deal. But when we look at nitrogen, nitrogen minus 3, it's electron rich. And so we got ammonium. We have this one. Dude, I can't believe it. Mercury. This one's called mercury. Mercury 1. So let's look at anions. Anions, we have monatomic anions. Monatomic anions would be like, we just change the ending to IDE, I. And so we got chloride, fluoride, sulfide, etc. Nitride. And then we have polyatomic anions. Polyatomic has 3 endings. We have IDE, we have ATE, and we have ITE. Those are the 3 endings. For the IDEs, you just memorize these. What polyatomics end in IDE? Hydroxide, cyanide. You know this one? O2 2 minus? Peroxide. Okay, the 8s. The 8s, we have 2 types of 8s. One from a pattern, the other from just straight memorization. Let me just write down the pattern really quick. The pattern for the 8s looks like this. We start off with BO3 3 minus, CO3 2 minus, NO3 minus, blank, ClO3, or no, FO3 minus, ClO3 minus, BrO3 minus, IO3 minus. Okay, that's one. This one's called borate. Remember that. And then the other pattern is this. The other pattern starts with SiO4, 4 minus. This is called silicate. And then it goes to PO4, 3 minus, SO4, 2 minus, SeO4, 2 minus, ASO4, 3 minus. Do you see the pattern? And so all these we can memorize easily. And then the rest, the other ones that we have to just plain old straight memorize are things like MnO4 minus, permanganate, CrO4 2 minus, chromate, Cr2O4 2 minus, etc. And then the rest, the ites are just, one less oxygen. And so those, let me just do this really quick. Those are like this, per 8. 8, ite, hypo, ite. And so all these have the same charge, just the number of oxygens varies. So this is +1 oxygen, -1 oxygen, -2 oxygens, same charge. And so we try to use patterns to minimize the amount of memorization that we do. Okay, I'm going to stop here. But some of these we just have to plain old memorize.